Hi everyone. We would like to present our final project for the machine learning class for spring of 2017, titled SVM Painting Style Recognition, presented by Artem Dovzhenko and Neol Konagai.
Hello, everyone.
Our inspiration for this project is that we are both interested in computer vision, and on top of that, I have taken one class on history of art.
So to start with, the dataset that we used was scraped from wikiart.org. Originally, we were planning to use official wikiart API to retrieve all the images and labels. However, unfortunately, wikiart administration have answered to our email very late, actually a couple of days ago. So we had to use some side project of a GitHub user, Lucas David, who provided JSON metadata in his GitHub repository. So once we downloaded that, we found out there are approximately 4,000 data for images. However, not all of the images were applicable for our purposes. We downloaded around 1,596 images, and you could see in this table the distribution of classes. As you can see, romanticism has an obnoxiously high number of 901, which is more than 50% of our data, so we had to reduce the number of images of that style. Also, another limitation that we found was that there were too few images of such classes as cubism, surrealism, and art informal, so we had to remove them from the dataset whatsoever. So in the end, we used a dataset compiled by ourselves of 500 images and 4 classes: Romanticism, Renaissance, Expressionism, Realism, with approximately 100 to 150 images each.
For the purposes of our project, we have selected 50 features that we base off of a paper co-authored by Li and Cha, who are 2 researchers for computer vision. The first 23 features relate to the color features of the image. The reason why we believe that these features are better representation for the paintings themselves is because we first agree with the assumption that we can use the color palette and other compositional features to predict the image style. And second, we believe that we would lose data by resizing the images to a standard pixel number. The first 23 features are the average hue for the whole image, the average saturation, the number of quantized hues, which means we take 20 bins in which we separate the hue pixels that fall into these 20 bins. We select the largest bin, the number of pixels in the largest bin, multiply by 0.1. Basically, we take the 10% of the largest bin number, and whatever bin that has larger than this threshold, we count them as into this number of quantized hues feature. And the 4 to 23 hue distribution is the pixel value, pixel number of the aforementioned 20 bins.
Moving on to the next 12 features are the composition features, which are detrimental for our project. Basically, in these features, we separate the image into 5 segments using watershed and k-means segmentation. The features 24 to 26, as you can see, are horizontal coordinates of the 3 largest segments out of those 5 segments that I just mentioned. 27 to 29 is the vertical coordinates. Features 30 to 35 are the values that relate to the variance and skewness of the mass centers for each of the largest segments. After we have successfully separated the image into 5 largest segments and chosen the 3 largest of them, we can retrieve average hue, saturation, and brightness or value in HSV parameters for the 5 of the largest segments. We have not mentioned yet that all of the features that we have just presented are normalized and fall from 0 to 1.
As we mentioned in the features section, a lot of the features depend on watershed segmentation, which uses k-means for segmenting different parts of the image. On the right side, you can see an illustration of the segmentation process. First, we take the local gradient, which means that the pixel values that differ from each other and they are side to side next to each other that will give the highest local gradient. The markers were found through SK images, morphological transformations, and we use also watershed segmentation function of SK image to find a segmented image. As you can see, this segmented image highlights the upper body of the figure represented on the painting, as well as the head and the arms. The ground is separated in a different color. The colors are only representation of the areas, segmentational areas.
On this slide, we could see sample output from the training of a support vector machine with 4 classes mentioned on top and 500 features from the images that we mentioned in the very first slide. The accuracy of 31% is not to be claimed a breakthrough, nor what we expect it to be, but we believe that there are several limitations that obstructed our way to success. One of them being this small number of images that we used, and the second being issues with watershed and k-means segmentation that will be discussed in the next couple of slides. In the parameters below accuracy layer, we could see that most of the parameters are actually the default parameters offered by the developers of sklearn platform, except for the error parameter C, which was raised from 1 to 10. For the training of this system, we used 7-fold cross-validation package, and it proved to be quite successful.
As we mentioned, the first limitation relates to the quantity of our data set. We have used 500 images from a larger data set of 4,000 images, which has been cleaned. As we've received now the official documented API for WikiArt, we are able to collect more images and clean the data. However, this process did not match up with our timeline. The next limitation that we have relates to the watershed segmentation, which we have studied for a little bit, but we hope to study it further. As you can see, the two images apparently seem the same. However, the image on the left side, painted by Grant Wood, American Gothic, has smaller number of pixels than an image on the right side, and it has effects in the way watershed segmentation finds the segments of the image. As you can see, the woman figure on the image on the left side, her vest does not get recognized by the watershed segmentation, but the same algorithm recognizes her vest on the right side. And the algorithm starts to recognize the glasses of the male figure on the right side, which is not recognized on the left side. In conclusion, implementing these two improvements, our algorithm could work better in the future. Thank you very much.
Thank you for staying with us till the end of this presentation, and goodbye.